algorithms, and later on we are going to start discussion about the what is the data structure, what are the different type of the data structures we have. And first, let us try to understand the theoretical implementation about the data structure, and then we will go for the implementation. So this is the sequential order what we are going to follow. Now see, what is algorithm? So before going to tell you a technical definition, in simple words, algorithm is nothing but a step-by-step procedure. So if you want to do any task, we need to follow some steps. For example, if you want to prepare a tea, what is the steps we need to follow? Nothing but purchase the milk, pour the milk into the bowl, add tea powder, sugar, stir it, and take the tea. So nothing but these are the steps. So if you want to do any task, we need to follow some steps. Sequential order is important. So like that in the computer science also, if you want to do any task, if you want to perform any operation, we need to follow some predefined steps. That is called algorithm. See now, a well-defined computational procedure. Algorithm is a well-defined computational procedure that takes some value or set of the values depending on the requirement as input and produce some value or set of the values as output. So let me simplify this. So algorithm is nothing but we need to follow some well-defined procedure, as I said, well-defined steps that is used to compute something. We need to follow some steps depending on the requirement. For example, if you want to find a sum of the two numbers, the steps are receive two numbers and implement addition operation like result equals to number 1 plus number 2, some logic, and generate the result, give the output. Like that, we need to follow some steps. And to implement this, we need to take some inputs that might be single input or multiple inputs depending on the requirement. And after performing the logic, that program is going to generate an output and that will be displayed. This is about algorithm. Okay, it is a computational procedure. Take the input, process the input, and give the result in the form of the output. In simple words, algorithm originates from the Latin word algorithmi. The word algorithm originates from a Latin word. The Latin word is algorithmi. First time the word algorithmi used by a Persian mathematician. That scientist name is Al-Khwarizmi. The scientist name is Al-Khwarizmi. The first time the word used by this Persian mathematician. Then coming to the characteristics of an algorithm. While you are working with algorithm or while you are writing some algorithm, developing an algorithm, what are the rules we need to follow? How the algorithm should be? What are the characteristics you must understand before developing an algorithm? First one is finiteness. Terminates after a finite number of the steps. So when you are designing any algorithm, that algorithm must be terminated after a finite number of the steps. The steps should be finite. Might be that steps are 6 steps, 10 steps, 20 steps, whatever it might be, that should be finite. As a designer of the algorithm, you must know when it is going to terminate, when your algorithm is going to terminate. If that may have the infinite number of the steps, we should not call it as an algorithm. Algorithm must have finite number of the steps only to give the result. Second characteristic is definiteness. So what is the algorithm we are going to design, or you design already, that must be designed in such a way that should have clear information and that should not have any confusion. Each and every step should be clearly you must mention in the algorithm, and that must not create any confusion. That is second characteristic of the algorithm. Third characteristic is input. As we covered just now, the definition of the algorithm, that algorithm must take input and process the input or inputs and produce the output. So input is nothing but any valid value, valid inputs. Those are clearly specified. So to your algorithm, what is the input? For example, might be number is the input for some algorithms in the case of the to find out some of the two numbers. Otherwise, if you want to work with any string values, input must be a string. For example, enter your name. If any program prompts the user to enter any name, the input is a string name. So that's why in the designing of the algorithm, you must specify what is the output, what is the type of the output, how many inputs your algorithm is going to receive. That is clearly specified. You must specify that clearly. Fourth one is output. So when your algorithm receiving the input, as per the logic we mentioned in the algorithm, that will be processed and produce the output. Your algorithm must produce the correct output for the given valid input. So whatever the input you receive, as we covered just now, depending on that, your algorithm logic must be work and that must reach a valid correct output. And you remember, each and every algorithm must produce at least one output. Without output, if you write any steps, for example, as we covered, the definition is a well-defined steps. But if you write any well-defined steps, that is finite and definiteness, but that is not giving any output, we cannot call it as an algorithm. Your algorithm should be finiteness, clearly, without confusion, with predefined and clear input and clear output. Fifth one is effectiveness. What are the steps we mentioned in the algorithm? Every step should be effective. For example, I have written an algorithm with 10 lines, let us say. Whatever the result we can get to execute those 10 statements after writing the program, depending on that algorithm, we can get the same output by executing 7 lines only. Nothing but what I want to say is, in the 10 lines, 3 lines are not effective. If you are not write those three statements, we can get the same output without affecting anything. Be effective. That is a wasting of Now, what is pseudocode and what is flowchart? Coming to the pseudocode is also used to describe the steps involved to do a particular task. And how to write a pseudocode? Pseudocode is a mixture of the natural language. Pseudocode is a mixture of the natural language plus programming constructs. So here the point we need to understand when coming to the a pure algorithm, algorithm is an independent construct of any programming language. We don't use any programming language related terms or any syntactical rules in the algorithm. But sometimes if you want to specify some particular programming constructs, programming related tasks in the form of the algorithm is very difficult. For example, looping concepts, multiple iterations a particular loop have. So to specify that type of the constructs by using a normal text, it is very difficult. That is one of the drawback of the algorithm. That's why we can use pseudocode, where in the pseudocode we can use any language like English, any language, not only English, plus some programming constructs. Nothing but where we feel it is not possible or it is very difficult to represent by using the natural language. In that case, we can use programming constructs. And that programming construct is not relevant to any particular programming language, general method. So in such a way, we can represent the steps very clearly with the help of the pseudocode. You can use some mathematical representation. You can use some programming related constructs like C assignment A plus B. Or if you want to specify the functions, arguments. So without using the constructs like this, it is very difficult to represent everything in the form of the text. So this is the advantage of the pseudocode. Okay, the next is flowchart. As of now, we covered algorithm and pseudocode. Overall, those two are used to describe the steps, predefined steps, well-defined steps. Coming to the flowchart, for example, let us say we have a pseudocode or algorithm with 100 lines. So reading the 100 lines and understanding the concept it takes some time because 100 lines of the statements that algorithm has. But we know that already for the human beings to read the 100 lines is very difficult, but human can understand it very easily if we represent the complete text in the form of any visualization, any images. So based on that, the concept flowchart was developed. This is the graphical representation of the algorithm or pseudocode. So by seeing that flowchart, you can easily understand what's happening in the program. What are the steps we need to follow? That is about flowchart. So using the geometric shapes containing description of algorithm steps. For each and every step, we use some geometric shapes. For different tasks, we use different shapes. For example, if a particular statement is related to the input, we use parallelogram. The shape we used parallelogram to represent that is a input related statement. For example, we have some processing related statements. C assignment A plus B. This is one process because a logic that should be executed by processor. For that, we use rectangle shape in the flowchart. Another example, suppose if you want to take any decision, if A greater than B, print hello, let us say. So if A greater than B is a decision making statement, that might be true or not, depends on the values of the A comma B. Right? So for that, we use a diamond symbol. So like for each and every statement, different type of the statements can be represented with help of the different geometric shapes. That is flowchart. So in the while you if you want to develop any project, generally the steps we follow is first we need to write an algorithm that is independent of any programming language on the paper in general. And you can represent it in the form of the pseudocode also. After that, you can use flowcharts to understand what's happening in your project or in your program. Whenever we have the clear picture about the program or project, then you can go for the implementation of the developed algorithm using any program. Generally, this is the scenario we can observe while developing the project. Next, algorithm complexity and how to find it. An algorithm is defined as complex based on the amount of space and time it consumes. Algorithm complexity means it is used to define based on the amount of the space and the amount of the time taken by the algorithm, consumed by the algorithm. Hence, the complexity of an algorithm refers to the measure of the time, the measure of the time that algorithm will need to execute and get the expected output. So just now as we covered the definition of the algorithm, it takes the input to process it and it gives the output. How much time that algorithm takes? That is what one of the complexity factor. Time complexity, the technical term we use, time complexity. Next, the space the algorithm will need to store all the data. So for example, if we develop the program after completion of writing the algorithm, we need to write a code. In that code, we need to use variables, some objects, receive the inputs, implement the logics, and store the outputs in another variable and so on. For that, we need to use space, memory. And how much space your algorithm is going to consume, that is called space complexity. In simple terms, how much space is required to execute your algorithm, your program. That is called space complexity. So these two factors define the efficiency of an algorithm depending on these two factors. What are those? Time complexity and space complexity. The efficiency of an algorithm will be decided. Your algorithm taking less time to give the output. So we can say that that is a good algorithm, efficient algorithm. For example, we have two programs, two algorithms. Those two are used to implement the same task, let us say. Requirement is same. Finding factorial of a given number, let us say. That is the requirement. We developed two algorithms, different algorithms. And algorithm one takes 2 seconds, let us say. Algorithm 2 takes 4 seconds. First algorithm takes 2 seconds and second algorithm takes 4 seconds. The concept is same, finding the factorial of a given number. So by comparing the time consumed by the algorithm to generate the output, the algorithm 1 takes less time compared to the algorithm 2. So in such cases, algorithm 1 is very efficient, that takes less time. So like that, depending on the time, we can decide which one is efficient. The two factors of algorithm complexity are time factor, space factor, as we covered. Time is measured by counting the number of key operations, such as comparisons in the sorting algorithms. Space is measured by counting the maximum memory space required by the algorithm. How much memory is required in max? How much memory maximum utilized by your algorithm is called space factor, or you can say space complexity. And how many number of the operations involved in that is related to the time factor. The next important topic related to this analysis of algorithm is order of notation. What is this, and what are the different types of the order of the notations we have? When it comes to the analyzing the complexity of any algorithm, when it comes to the analysis of the complexity of any algorithm in terms of time and space, as we covered, the algorithm affected by the two important factors, those are time and space. So we can never provide an exact number to define the time required and the space required by the algorithm. This is very, very important part. We can never provide an exact number to define the time required and space required by the algorithm. Nothing but, so whenever you design the algorithm, we cannot say the exact number. We cannot say like this algorithm take 2 seconds and this algorithm takes 5 MB memory. Exactly, we cannot say that. Okay, for understanding purpose, in some examples, we may take that, but exactly coming to the practical, we may not say like that because that has so many factors internally that needs to consider so many factors internally. That's why we may not give a exact number for the time complexity, even the space complexity also. Because let us say time complexity, when you are trying to execute your program, at that time, no another applications are being executed in your system, let us say, your processor may takes less time. See the another example, same code, I am trying to execute the same code in another system, but at that time, processor is busy to execute another process also, another applications also. In such cases, that may take more time. Our CPU processor speed also may be vary. So like that, different factors are there which affect the time complexity. That's why we may not give accurate number. So how can we express that? So we are saying that we cannot give an accurate number, a specific number for the time complexity and space complexity. Then how can we express that? So instead we express it in the form of the numbers. We can express it using some standard notations. As we are unable to express the accurate number, exact number, we can express space complexity and time complexity using some standard notations. Those notations are called asymptotic notations. Very, very important point. What is asymptotic notation? When we have an algorithm, there is no chance in practically there is no chance to give an exact number related to the time complexity and space complexity. That's why we can express those by using some notations that is called asymptotic notation. Those are called asymptotic notations. What are the notations we used? Those are called asymptotic notations. So we have different type of the asymptotic notations. Let us discuss those one by one. First one is big O notation, that is represented with capital O, uppercase O. It represents the upper bound running time complexity of an algorithm. The big O notation is used to represent upper bound running time. For example, I have an algorithm. In some cases, as I said just now, that might be depends on processor speed and free time of the processor, like that. So let us say one algorithm takes 1 second in some cases, or 4 seconds in some cases. So what is the upper bound limit is 4 seconds. So we are focusing about upper bound in this case. That is, we can represent that upper bound running time complexity of an algorithm with the help of the big O notation. Big O notation specifically describes worst case scenario. These technical terms are important. Worst case scenario. Worst case in the sense upper bound. We can execute the same code we can execute the same code in case one that takes 1 second, in case two that takes 4 seconds. So obviously 4 seconds is a worst case because that algorithm takes more time. So that is called worst case. And where that takes more time, upper bound time. So you can understand that big O notation is used to represent the upper bound running time, and that is the worst case. That is used to big O notation is used to describe worst case scenario. In worst case, that algorithm takes 4 seconds as per our examples. Few examples to understand how we represent the time complexity and space complexity using big O notation. For example, order of 1. We can express big O notation like this, order of 1. So order of 1 represent the complexity of an algorithm that always execute in same time or same space, regardless of the input data. What does it mean? It takes constant time, constant space. Order of 1 is generally that is used to represent the meaning, to represent that algorithm takes same time even though you changes input. Regardless of the input data, that takes the same time. In such cases, the space complexity or time complexity of that particular statement is represented with order of 1, constant time. Because even though you change the input, the time taken by the statement will not be changed. Right? For example, for more clarity, let me give an example regarding to the order of 1. See, if we have a statement like integer data type, number is a variable, assignment array of 5, where ARR array is my array name. I created one array, let us say. Okay. 5 represent index value. Okay. So what is the meaning of this code? I want to access the element which is available at the index 5 in the array ARR. Then I want to assign that to the variable number, NUM. So here, this step will always execute in the same time and it takes same space, regardless of the size of the input data. Right? Whatever it might be the size of the array, whatever it might be the value available at the index 5. This takes same amount of the time. The statement takes same amount of the time. And that takes same amount of the space also, even though if you change the values, input values. In one case, in the fifth index, I may store 10. In another case, let us say I may store 20, 30, and so on. Whatever it might be the data elements you changed in the index 5, but the time complexity and space complexity won't be changed because that doesn't depends on the values, input values in this case. In such cases, the big O notation, with help of the big O notation, we can express that the worst case scenario for that statement is order of 1. It's constant time in simple terms. Next case is order of n. This is the order of 1. Order of 1 means, okay. Coming to the order of n. Order of n represents the complexity of an algorithm whose performance will grow linearly in direct proportion to size of the input data. In simple terms, when you increase the input size of a particular algorithm, that takes more time. That algorithm takes more time. If you decrease the size of the input data of your algorithm, that takes less time. If you observe that type of the scenario in your algorithm, the complexity of your algorithm can be represented as order of n. Let me give a simple example to understand this point. The execution time will depend on the size of the array. When the size of array increases, the execution time will also increases in the same portion, in the same proportion. Traversing an array. Another example is traversing an array. Traversing is nothing but visiting each and every element. Suppose I have 10 elements in the array. To traverse those elements, it takes 10 seconds, let us say. And if I increase the input data from 10 to 30, in such cases that algorithm takes 30 seconds to traversing that array. So depending on the input size, the traversing time taken by that algorithm is changed linearly, right? If the input size increases, time also increased. Input size decreases, traversing time also decreases. If your algorithm has this type of the property, you can express the order of the notation of your algorithm is order of n, where n is used to indicate size of the input. Size of the input is n. Clear, I hope? No. So similarly, there are other big O notations such as logarithmic growth. In the previous case, that is linearly increased. Some we have different type of the algorithms. In that, some algorithms has the property of logarithmic growth. In such cases, the die complexity can be represented as order of log n. Then combination of log linear growth. In such cases, the order of that particular algorithm is represented as order of n log n. And depending on the input, there is a exponential growth for the time. In such cases, the big O notation we can represent like order of 2 power n. Order of 2 power n. So like this, depending on the nature of your algorithm, the notation will be changed. If I have to draw a diagram to compare the performance of the algorithms denoted by these notations, then I would draw it like this. See, order of one, it takes minimum time, and compared to the other time complexities, it takes minimum time. Then next, order of log n, same sequential order, it takes less time, and last one takes more time. That is the order. Okay. Order of log n, order of n, order of n log n, order of n square, order of n cube, order of n power 4, and so on. And finally, order of 2 power n. So this is the hierarchy from where order of n takes less time, order of 2 power n, last one, takes more time. So this is about big O notation. So if we draw the diagram depending on the different complexities as I covered just now. So these are takes less time. And if you go to the top, those takes more time. Nothing but see, this is worst case. Worst case, in this case, the worst means take more time. Bad, fair, good algorithm, best algorithm. Okay. Now, omega notation. Second type is omega notation. Omega notation specifically describes the best case scenario. So just now we covered big O is used to describe worst case scenario. Okay. And this is omega. It is used to specifically describes the best case scenario. It represents the lower bound running time complexity. Observe the word lower bound running time complexity. Big O is used to represent upper bound running time complexity. Now here, omega notation, it is used to represent lower bound running time complexity of an algorithm. So if we represent a complexity of an algorithm in omega notation, it means that the algorithm cannot be completed in less time than that, what we represent. For example, I have an algorithm and I'm representing that the omega notation of that particular algorithm is 2 seconds, let us say, to make the concept clear. 2 seconds means at any cost, we cannot run that algorithm less than the 2 seconds time. That is the meaning of omega notation. If we specify omega notation value is 2, we cannot specify the exact value as we covered just now, but to make the concept clear, I am using that. 2 seconds means we cannot execute that algorithm less than that particular time. That is what? Lower bound running time. Minimum time. Minimum time is 2 seconds. It would at least take the time represented by omega notation, or it can take more when not in the best case scenario. Third category, theta notation, represented with theta symbol. This notation describes both upper bound and lower bound of an algorithm. So we can say that it defines exact asymptotic behavior. In the real case scenario, so theta notation describes both upper bound and lower bound of an algorithm. So we can say that it defines exact asymptotic behavior. So in the real case scenario, the algorithm not always run on best case, that may not run always in the worst case. So this is average case. The average running time lies between the best and worst, obviously, and it can be represented by the theta notation. So as we covered, the execution time may be vary from time to time depending on the system. We covered big O notation best case and omega notation worst case. So big O notation worst case and omega is best case, less time. Big O is used to represent the upper bound limit, and omega is used to represent the lower bound limit. But that may not be possible all time. The system may not take less time, that may not take very lengthy time, maximum upper bound time. But its best suitable case is average time. That may take the time lies between best and worst in general. So we can represent that average case time with help of the theta notation. So that's why it is very useful for us. So that is about analysis of the algorithms. What is algorithm? What is flowchart? What is pseudocode? And characteristics of the algorithm we covered. After that, how to analyze the performance of the algorithm we covered. We consider two important factors. Those are space and time. That is time complexity and space complexity. And in that also, we cannot express complexity of an algorithm by using any certain number. So for that, we use some notations. We discussed about three notations: big O, omega, theta. Those are used to represent worst case, best case, average case, respectively. Now, coming to the next topic, data structures. What are the different data structures we have, and what are the difference among these different data structures, and what is the structures they maintained, and how can we do some operations with that? So these points we are going to cover here. So before start the different type of the data structures explanation, let us try to understand what is a data structure actually. How can we define that? Data structure can be defined as the group of data elements. The data structure can be defined as the group of data elements, collection of the data elements, which provides an efficient way. This is important point. The efficient way of storing and organizing, of course, receiving also data in the computer so that it can be used efficiently. In simple terms, let me explain this definition. With the help of the data structure, we can store the multiple elements, collections, a group of the elements in easy way, in effective way. We can store that, organize that, and retrieve it whenever we require. For that, we use data structures concept. Data structures can be defined as the group of the data elements which provides an efficient way of storing and organizing the data in the computer so that it can be used efficiently. Let me give some examples for the data structures. Arrays, linked list, stack, queue, and so on. We have different data structures also we'll cover in the coming sessions. Data structures are widely used in almost every aspect of the computer science. Operating system, we can use data structures in the operating system also. Suppose I'm using Windows operating system now. So the developers, the Microsoft also use data structure concept to develop Windows operating system. Okay. And compiler design. So whenever you work with C language, we use compilers not to execute the code. So to develop the compiler also, we need to use data structures. In the artificial intelligence concept, graphics, and many more, of course, in the database also. So probably we use data structures in all the computer science applications. Advantage with data structures. As I covered, efficiency is the main advantage with data structures concept. Efficiency of your program depends upon the choice of data structures. What type of the data structure you choose, and depend that the efficiency will be decided. For example, we have some data and we need to perform the search for a particular record. We have some data and we need to perform the search operation. We need to find a particular record. In that case, if we organize your data in an array, we will have to search sequentially, element by element. Hence, using array may not be very efficient here. There are better data structures which may take the search process efficient, like binary search tree or hash table. So let me simplify this point. Suppose if you create an array where you have 100 elements, the first element is 1, second element is 2, and 100th element is 100, let us say. So I want to search for an element for 99. I want to search for an element 99. I want to know whether 99 is available or not in the given array. And coming to the searching mechanism in the array, that is sequential mechanism. So we need to select for the required element in the index 0, index 1, index 2, index 3, and so on, index 99. We have 100 elements now, index is ends with 99. So like that, we need to compare our required element with all the elements, all the index values. We know that the required element is available at the 99 position. The index value is 98. We need to go through 98 elements. We need to pass 98 elements. That takes more time. But we have different type of the data structures where we no need to follow sequential mechanism. Directly, we can access that required data by following some implementation methods like hash tables, search trees. We'll cover later on. So those takes very less time because the searching mechanism is not in the sequential order. So like that, the point is depending on the data structure we implemented, the efficiency of the algorithm depended. Okay. Reusability. Data structures are reusable. That is, once we have implemented a particular data structure, we can use it at any other place in our project. Implementation of data structure can be compiled into libraries and which can be used with the different clients. If you're working with any company, once you developed a algorithm for any data structure, you can use same data structure for the different purposes. Next advantage is abstraction. Data structure is specified by the ADT. Abstract data types. ADT means we'll cover later on, which provides a level of abstraction. The client program uses the data structure through interface only, without getting into the implementation details. In simple words, when you are working with the data structure concept and if you develop any user interface, the person, the user who are working with that user interface doesn't have the knowledge about the implementation of any data structure. He knows what that user has to enter and what he will get. That's it. What is the input the user has to give to the code and what he is expecting. That output will be delivered to that person. But that person doesn't have any idea about the internal implementation. That is what abstraction here. And let me give a simple example to understand this case. For example, if you visit any restaurant, let us say, you order some dish, whatever it might be, XYZ. After some time, that ordered dish will be served to you, will be delivered to you, will be served to you. But you don't know what's happening in the cooking room, right? But of course, you are not allowed to, anyone may not have the permission to enter that cooking room in general in the restaurants. But here, what I want to say is you are giving the input, you are giving the name of the dish, and you are getting the output. That dish will be delivered to you and served to you. But you don't know, as a customer of the restaurant, you don't know what's happening in the cooking room, whether that is made with some ABCDs or whatever it might be. Whatever they use, you don't know in simple terms. That is what abstraction, hiding the implementation but providing the result, is called abstraction technical. So by using the data structure also, we use ADT, abstract data types. We specify what are the operations we implemented and what are the inputs required and what is the output given by the algorithm. So everything remaining is hidden from the user. That is what abstraction. Now coming to the complete structure about the data structures, hierarchy of the data structures. We have two major categories in the data structures. Those are primitive data structures and non-primitive data structures. Generally, primitive data structures, or you can say primitive data types also. Okay, these are used to store single elements. Individual elements you want to store, you can go for the primitive data types or primitive data structures. non-primitive data structures. And coming to here, again, we have two categories, linear data structure and non-linear data structures. Linear data structure and second one is non-linear data structures. So generally, we need to maintain the data in the linear form here. And in the non-linear, we may not maintain the data in the linear form. We may follow different methods, different structures. We'll cover later on. And coming to the linear data structure again, we have two categories, static linear and dynamic linear. Once you created, you may not change that. Even though those are stored in the form of the linear, once you created, it is not possible to change it, or that may take a lot of uh, instructions to change the organizing of the data. Those are static, and example is RRA. Coming to the dynamic, dynamically we can store the data, and in the linear form, the data will be stored. Example for that, linked list, stack, and queue. In these data structures, we can store the data linear fashion, and dynamically we can change the data elements. Next, another hand, we have non-linear data structures where the data elements are not stored in the linear form. Generally, we form tree structure form, step by step. In that, we have two data structures, tree data structure and graph. These two are non-linear data structures. And finally, as a basic level, you must remember linear data structures are array, linked list, stack, queue. These are the linear data structures. Coming to the non-linear data structures, tree and graph are non-linear data structures. This is very, very important point, very frequently asked question in the exams also. Linear data structures and non-linear data structure. In the linear data structure, the data elements are stored in the linear fashion. And in the non-linear data structure, we are not following the sequential order. The elements are followed in the different styles, step by step, are just like a tree structure. Okay, different structures we follow. And primitive elements means single element. Data structures means multiple elements. As I covered, the definition of the data structure is multiple elements or group of the elements we can store, we can organize. So see, primitive data structures are int, float, character, pointer. So in these primitive data structures, we can store only single value. If any object or data type of int we have, we can store only single value in that. In the float also single value, character, pointer, all are. And coming to the linear data structure and non-linear data structure, a data structure is called linear data structure if all of its elements are arranged in the linear order, sequential order. In linear data structures, the elements are stored in non-hierarchical way. There is no hierarchical way we are following here. As I said, non-hierarchical way where each element has the successors and predecessors except the first and last. Obviously, right? We start with first, there is no previous element for that, and for the last element, there is no next element. Except these two, every element has previous and next element in simple terms. So Finally, you must understand that in the linear data structure, the elements are stored in the linear order. There is no hierarchical method is followed. Every element has a previous element and next element except first and last. Coming to the non-linear data structures, this data structures doesn't form a sequence. It doesn't form a sequence. It doesn't store the elements in the sequential order. Each item or each element is connected with two or more other items in a non-linear arrangement. One element may have the connection with more than one element, but in the linear manner, one element, next element. That's it. One element is connected with the next element only, direct connection. But coming to the non-linear, one item have the connection with two or more elements in non-linear arrangement, in the non-linear fashion. The data elements are not arranged in the sequential structure in non-linear data structure, right? So this is about types of the data structures. In the coming session, next session, we start the discussion about what are the data structures we have in the linear data structure. Like a stack queue we have, we'll start the discussion about those in the next session, right?